Hello, and welcome to a lecture in which we will present an example of geometrical optics aperture integration analysis of an axisymmetric paraboloidal reflector. I'm Steve Ellingson. Here's an overview of this lecture. First, a problem statement for the example that we will consider. This will be primarily an exercise in verification of datasheet values. So we'll look at a datasheet and then we'll see if we can recreate or justify the values that appear in the datasheet. We'll talk about how to select a method. And the two methods that will emerge here as natural choices will be physical optics surface integration and geometrical optics aperture integration. We'll end up going with the latter, and I'll explain why. Then I'll show you the results. And these will come in two passes. The first pass will just use a very simple feed model and show what happens. And the second pass will account for some more sophisticated effects, in particular, aperture blockage and feed efficiency. And then finally a summary, in which it becomes clear that feed design is an important aspect of these systems. So here's the example that we'll consider. This is a commercially available dish. It's an axisymmetric paraboloidal system. It's 1.8 meters in diameter. So the distance from here to here is 1.8 meters, and that's a quantity we've been calling D. The F/D ratio is given as 0.42, a very typical F/D ratio that falls within the typical range of 1/3 to 1/2 that we normally see. Here it says the focal point is 760 millimeters. What that really means is the focal length, F, is 760 millimeters. And recall that given the focal length and the F/D ratio, we have completely specified this axisymmetric paraboloidal dish. Now here's the thing we're interested in checking up on. The gain of this dish at 1.69 gigahertz is specified to be 27.5 dBi. And we'd like to see if we can recreate that result. So, as I mentioned at the beginning of this lecture, there's two ways we can go about this. Plan A, very common way to go, is physical optics surface integration. In other words, we treat the problem as a scattering problem where the feed creates the incident field and the dish is the scatterer. We use what I've been calling type 2A equivalents, and this yields only equivalent surface electric currents, not magnetic currents, according to the physical optics approximation. So the steps look like this. First, we compute these equivalent electric surface currents using the relationship J equals 2n cross Hi, where n hat is the normal to the surface at the point at which we're computing the currents, and Hi is the instant magnetic field intensity at that point. And we consider this only over the lit surface of the reflector, and we say it's zero otherwise. So in other words, we don't account for currents on the backside of the reflector because that's not part of the lit structure. Given the electric surface currents, we can compute a magnetic vector potential. This is a far field expression, of course. And then from the magnetic vector potential, we can compute the far field electric field associated with that simply by removing the radial component, which we know is 0 in the far field, and then tacking on a minus j omega. Plan B, and the approach we will actually use, is geo plus aperture integration. The idea is this. We have the feed right here. We know from geometrical optics how the scattering from the reflector should work. At each point in the reflector, we'll have an incident ray and a reflected ray, and we know, because this is an axisymmetric paraboloidal reflector, that all those reflected rays are traveling in the same direction. So then we define an aperture in front of the dish, over which the geometrical optic fields are non-zero. We know outside this aperture, that is this projected surface in front of the dish, that there are no fields, at least according to geometrical optics. So it suffices simply to integrate over this blue region in order to determine the scattered fields, the fields radiated by this structure. So the game plan is calculate the geofields at the disk, get the pattern by integration over disk for each field point. That's classical aperture integration. And then get the directivity by one integration over the disk. So if we want the patterns, we have to do an integration over the disk for each field point. If all we need is a directivity, then we only really need one integration over the disk. And we've talked about how to do that numerous times in the context of aperture theory. Just to remind you, the appropriate expression to use in this case would be the one I've written here, the electric field, in terms of spatial Fourier transforms of the various components of the magnetic equivalent currents. So which one should we use and why? Well, first let me say for axisymmetric reflectors, both techniques, physical optics surface integration and geometrical optics aperture integration, yield nearly identical results. And of course, what we're saying here is that this is true where both methods are valid, which is in front of the reflector. The further away we get from the main lobe and the first few side lobes, both methods are expected to deteriorate and become invalid. However, in the region where they are both valid, they should both give, again, nearly identical results, and with about the same computational burden. They both involve surface integrations. Conventional wisdom is that physical optics surface integration is preferable to GeoAI for offset-fed reflectors. So this is this class of reflectors in which the paraboloidal section is not axisymmetric and the feed is down here somewhere. So you have rays that look like this. Now the reason why this is so is not entirely rigorous. It's based on some experience, and perhaps we'll discuss this in more detail later. But here we don't have an offset-fed reflector, so in principle either method is okay. The reason we lean towards GeoAI is because it makes explicit the theoretical connection to aperture theory. And that can yield useful insight, and I'll show you some examples of that in this very lecture. So let's choose this approach for the present problem. Skipping to the end, here is the result. So this is GeoAI applied to this particular dish, and what I'm showing here is the magnitude of the normalized field pattern as a function of theta, which is measured from the axis of this paraboloid. So recall that the system that we use, the global coordinate system, has z hat in this direction, the origin at the focal point. So theta is being measured with respect to the center of the main lobe in this particular system. So this is maximum directivity here, and then 90 degrees is perpendicular to that direction. And then I'm showing E-plane copole. Now first remember that this region that I've indicated here is not expected to be accurate. This is a feature of both of the methods that we considered a little bit earlier, certainly true of this particular method. In this range, however, we would expect pretty good accuracy. Now first I should let you know that when I computed these results I had to assume something about the feed. So I assumed a vertically polarized feed with an isotropic pattern. So this isn't even a Hertzian dipole, this is a vertically polarized current element which somehow magically has an isotropic pattern. And that's just a starting point, just to see how things look. A very common technique, start off with the simplest thing that you can do that's not wrong, and then add detail as you need it to refine your results. So when we use this method, GeoAI, with this particular feed, what we find is that the half-power beam width is about 6 degrees. That's this distance here. And that's, of course, measured to 3 dB points. I guess I should draw it this way. The first side lobe level, or the level of the first side lobe, is minus 19.5 dB. So that's that distance right there. And we would expect this to be a fairly accurate guess, at least within the constraints of these assumptions. And when we calculate directivity using the aperture integration method, we find a value of 29.95 dB. Now, this is somewhat higher than expected from the data sheet. The data sheet value was 27.5 dBi. And this is, of course, dBi as well. And so there's a significant difference, something like 2.4 dB difference. So we would like to try to understand that difference. I mean, first we see the results aren't completely ridiculous, but 2.4 dB is something that's worth considering in the context of an engineering problem. So let's see if we can understand what the differences are. So the first thing we can do is a sanity check. And the sanity check here is we'll just assume a uniform 1.8 meter aperture. In other words, we'll do the exact same problem, but here we'll assume that the magnitude in the aperture is constant and the phase in the aperture is constant. Now, in the actual problem, we would expect the phase to be constant in the aperture, but certainly the magnitude isn't constant in the aperture. So this might be one way that we can account for the difficulty. And the advantage of employing a uniform 1.8 meter circular aperture here is that we have ready-made analysis and results from classical aperture theory. Here's the result. So for a uniform 1.8 meter circular aperture, we find this result for the normalized field pattern. We can recompute the metrics that we computed in the previous scenario. We find that the half-power beamwidth is 5.8 degrees, just slightly narrower than 6.0 degrees, which is what we had before. And the side lobe level goes up a little bit. This was about minus 19.8 dB in the previous scenario. And the directivity goes up to 30.07 dB, as we would expect if the aperture magnitude is uniform. So as a sanity check, this seems to be confirming that our analysis done in the previous scenario is valid. So this is not explaining the missing 2.4 dB. It's simply saying that under the assumptions that we made before, we appear to have worked the problem correctly. So now we have to look for some other mechanism to account for the missing 2.4 dB. Now, one mechanism that you might consider is feed blockage. Note here that there is this structure, the feed itself, which blocks part of the aperture. Now, just eyeballing this picture, I estimate that this diameter that's blocked is about 0.2 meters. In other words, 20 centimeters. And if you do the math, you find out that that's about 1.2% of the area of the aperture. Now, a simple calculation here says that should result in about 0.05 dB of power loss. So it seems unlikely that this can account for a 2.4 dB difference that we observe. Nevertheless, it's simple to analyze this problem. What we can do is we can repeat the GOAI calculation and just put a hole in the middle of the aperture of about that diameter and see what happens. So here we are with this simple blockage model, and here is the new result. What we find is the half-power beamwidth is hardly affected, and that's expected because half-power beamwidth should depend primarily on the overall dimension of the aperture, not about details internal to the aperture. The side lobe level is different. It changes a little bit, but that difference is relatively small, so there's nothing really to interpret there. And the gain goes down very, very slightly. And this is exactly what we anticipated, that the gain should just go down very, very slightly from what we had in the previous scenario. So, half-power beamwidth hardly affected. We could have anticipated that. Side lobe levels are perturbed slightly. Not only is the first side lobe level changed, but some of these side lobes are going up and down. And that's just an artifact of putting a hole in the middle of this aperture. And then the gain is only very slightly reduced, and we in fact anticipated a value very close to this based on this very simple consideration of the amount of area that was taken out of play by the blockage, by the feed. So feed blockage does not appear to be a reasonable way to explain the missing 2.4 dB. So where is the missing gain? Well, first, as I noted here, clear that the blockage can't account for all of that missing gain. It can only account for a tiny reduction in the directivity. There's still 2.4 dB unaccounted for. So let's make a list of the things that could possibly account for the missing gain. One is feed impedance mismatch. This is a tempting theory. I will tell you now, and we'll see by the end of this lecture, that this is normally negligible for these kinds of systems. It's pretty easy to make feeds that are well matched to the impedance of coaxial transmission lines, for example, over the bandwidths that these systems are normally designed to operate in. That's not to say that you can't imagine some other problem where this might become a problem, but in this class of applications, feed impedance mismatch is normally a negligible problem. Similarly, you might think, well, maybe there are ohmic losses in the feed that could account for this. So this is normally negligible because the feed can be made from all metal components. So that leaves spillover, over-illumination. This is a mechanism we've probably talked about in a previous lecture, and we'll address it in more detail here. And another theory is feed pattern taper, and that's the fact that the distance between the focus and the rim is greater than the distance between the focus and the vertex. So there's a reduction in magnitude as you get further out from the center of the aperture. So either one of these two things seem like strong candidates. So first, let's talk about over and under illumination. So this is a diagram from your book. It simply illustrates these two possible scenarios. On the left here, we have over illumination. And what happens here is the feed pattern is wider than the angle to the rim, so that some fraction of the power, namely that power there and that power that exists there in the pattern, is not intercepted by the dish and so is wasted. So in this case, we say that the spillover efficiency, epsilon sub s, is low, but the taper efficiency is high. In other words, this has the nice feature that we hit the rim with a relatively high level, so that the overall level across the dish is relatively high. You can see there's a built-in trade-off here. Whatever we do to make the level of power delivered to the dish high is going to result in more and more spillover. So these two things tend to fight each other. This particular condition is typical of inexpensive dishes with simple feeds and dishes with large F over D ratios. At the other extreme, we have under-illumination, where we say perhaps that spillover is a bad thing that we don't want, and so we make the spillover efficiency high. So in this case, we're showing a case where very little power ends up spilling beyond the dish. It's all inside the dish, but as a result, the power that is intercepted by the dish near the edges is relatively low. So we're not really using the dish very efficiently. Now this is typical in low side lobe applications. This has lower side lobes because the thing that creates side lobes is the edges of the dish, and the edges of the dish are being relatively less intensely illuminated in this particular scenario. And this, of course, is also a characteristic of dishes with small F over D. Okay, so let's do a ballpark spillover calculation for this particular dish. The starting point is this relationship between F over D and angle to rim that we've developed in a previous lecture. We know the F over D for this dish, so we can solve for the angle to the rim. We find it's 62 degrees. The reflector subtends a solid angle of 1.38 pi steradians. You can calculate that by knowing that there are 4 pi steradians in a sphere, and the amount of the sphere that we're actually subtending is 62 degrees divided by 180 degrees. That's a very straightforward calculation once you realize the geometry. Now, the directivity of a small feed, now we don't know exactly what's going to be in practice, but let's just start off with a typical value of 2. In this case, the associated beam solid angle, which is always given by 4 pi over the directivity, would be 2 pi. So the spillover loss should be the ratio of these two things, 1.38 pi steradians, based on how much of a sphere the reflector subtends, and then the beam solid angle down here. The ratio of those two things should give us an indication of the spillover loss. We get minus 1.6 dB. In other words, we assume that we're losing 1.6 dB of the power from an isotropic feed by virtue of the fact that the dish does not capture all of the power. There is some spillover. Now 1.6 is somewhat promising because that's a much closer value to 2.4 that we're looking for. We can also consider feed taper. Now here's how we can do this. A very simple feed is likely to have a pattern that goes as cosine theta f. Remember, sub f indicates the feed coordinate system. The edge taper you can then compute as being cosine theta naught, again that's the angle to the rim, which gives you a value of 0.4695, and that's minus 6.6 dB. In other words, the magnitude of the field that strikes the rim is about 6.6 dB below the value of the magnitude of the electric field which strikes the vertex of the dish. Now, we don't quite have the math that we need to do this yet. However, I will tell you, and you can actually look this up in any good textbook, that this equates to an aperture taper efficiency of about 0.92. In other words, this particular edge illumination, it's sometimes written EI, corresponds to a taper efficiency of 0.92 dB, which is minus 0.4 dB. So the evidence here is that feed taper, based on this calculation, appears to be a relatively small effect, at least compared to spillover efficiency. Now, this doesn't account for everything because we also have this 1 over r spreading, right? In other words, it's not just the magnitude of the field at the dish, there's also the fact that we have spreading from the feed point to the dish. And if we roughly say maybe minus 3 dB for this, just to do a calculation, that would reduce this value of 6.6 dB to 9.6 dB, and using the same method as in the previous line, we would get a taper efficiency that has to be greater than 0.88, which is minus 0.6 dB. So even for this very bold assumption here, we see that it really doesn't have that much impact on the taper efficiency. So based on this, we would expect a taper efficiency maybe somewhere between these two extremes. We could use a value of 0.5. And I'll also point out that this is relatively pessimistic, this value here, because the original integration already includes this loss. We account for that in the GeoAI technique by virtue of the GO part of the calculation. So this is relatively optimistic. This is relatively pessimistic. More likely result then is likely to be somewhere between them, or a value of minus 0.5 dB or so. So now we can put this all together. If we take the directivity assuming a uniform illumination from straightforward aperture integration, we get 29.95 dB. If we account for the loss due to blockage, we came up with a value of minus 0.05 dB, and we did that two ways, from a straightforward area calculation and then again from the actual electromagnetic calculation. So this appears to be a pretty solid number. We came up with minus 1.6 dB for loss due to spillover, and we came up with a value of minus 0.5 dB for loss due to feed taper. And if we add that all up, we get 27.8 dB. The datasheet value was 27.5 dB, so the difference is now 0.3 dB. And this makes good sense. Based on this calculation, we would say this data sheet is probably right, and we've accounted for all the things that are important here. Now you might ask, what's the remaining error, this 0.3 dB? And this is hard to say. We'd have to do more detailed analysis and maybe even some measurements to support that analysis. But it's certainly the cumulative error in the estimate of the spillover, the estimate of the feed taper, and plus there will certainly be some impedance mismatch and some ohmic loss. Can't make that zero, but that's, again, probably very small. So let's summarize. Directivity, gain, half-power beam width, and side lobe level of reflector antennas can be estimated with surprisingly good accuracy using simple methods. Spillover and feed taper have a big impact on gain. We have demonstrated it in this lecture. This is why feed design is a big deal for reflector antenna systems. In fact, I would say it's the primary problem in reflector antenna systems. Once you choose an F over D, or perhaps as part of the selection of F over D, you must consider the characteristics of the feed, because together the F over D of the dish and the characteristics of the feed will determine the spillover and feed taper, and we see that those two things have a big impact on the gain. Blockage, on the other hand, has a relatively small impact on gain. This is primarily an issue with side lobes. We saw the side lobes jitter around a little bit when we changed blockage. And we didn't consider this, but I'll tell you also that polarization purity can be an issue. Impedance mismatch and ohmic loss can normally be made negligible for this kind of system. This concludes this lecture, in which we've presented an example of GeoAI analysis of an axisymmetric paraboloidal reflector.